Now, welcome to the second talk for the day and the last talk for this seminar series. It has indeed been a pleasure for us to organize this fractional calculus seminar series. For the last talk, we have Professor Pablo Seleson, who is a research scientist in the Computer Science and Mathematics Division at the Oak Ridge National Laboratory, where he began as an Alston S. Householder Fellow. Dr. Seleson received both his bachelor's degree in physics and in philosophy and his master's degree in physics from the Hebrew University of Jerusalem in 2002 and 2006, respectively, and his PhD in computational science from Florida State University in 2010 under the advisement of Professor Max Gunzenberger. After graduation, he joined the Institute of Computational Engineering and Sciences at the University of Texas at Austin as an ICES postdoctoral fellow under the supervision of Professor J. Tinsley O'Oden, where he also worked in close collaboration with the Computer Science Research Institute at Sandia National Laboratories. Dr. Selson research focuses on multi-scale materials modeling and on mathematical and computational analysis of peridynamics and related non-local models with applications to computational fracture modeling. Dr. Selson is an associate editor of Applicable Analysis and editorial board of the Journal of Peridynamics and Non-Local Modeling, a member at large of the executive committee of the U.S. Association of Computational Mechanics, past chair of the U.S. ACM Technical Trust Area on large-scale structural systems and optimal design, vice chair of U.S. ACM TTA and on mathematical methods in computational engineering and sciences, and member of the Computational Mechanics Committee of the Engineering Mechanics Institute of the American Society of Civil Engineers. We are really happy to have you, Professor, here. You may please begin your talk.
Thank you very much. So thank you very much for the invitation and the kind introduction. It's a great pleasure to be here to talk about the coupling of peridynamics and classical continuum mechanics. So we'll do an overview, discuss some methods and analysis. So we start with some introduction to peridynamics, in particular to those who are not familiar enough with it. However, I will focus on the aspect of peridynamics that are specific for this presentation. Then we'll do an overview of coupling, discuss some coupling methods, show some coupling analysis, and then summarize. So the motivation for peridynamics is failure and damaging materials, and you can see here two famous cases of a catastrophic failure. And peridynamics, as other fracture methods, they try to model these things in order to prevent these catastrophic failures. Now, peridynamics is a generalized continuum theory based on spatial integration that employs a non-local model of force interaction. And the key feature is that there is no differentiability assumption on displacement fields. So overall in peridynamics, for each point here, do you see my cursor?
Yes, we do see your cursor.
Right. So for every point X in a body, in a continuum body, we assume that the point X interacts with a finite surrounding neighborhood, denoted by H sub X, and then X interacts through some force function F with all points X prime within some neighborhood of radius delta, and delta is a length scale in this non-local model. And the evolution of each point follows this equation of motion, where rho is the mass density, U is the displacement field, and we have on the right-hand side the total force density, including the internal force density through the integral over this force function F, and B is an external prescribed body force density. Now, F is what we call a bond force density, takes a pair of points X prime and X, and maps the vector connecting these two, we call it the bond, to force per volume squared. And we assume that F is going to be 0 whenever the 2 points are separated farther than the length scale delta. Now, peridynamics is a fast-growing field. It started in 2000 with a paper by Stuart Sealing from Sandia National Laboratories. And actually, we did an investigation on the evolution of the community in terms of co-authorship. So we built a co-authorship network in a publication together with Biraj Tahal and Jeremy Tregeser, published in the Journal of Peridynamics and Local Modeling. And we analyze the authorship evolution of Peridynamics publications, and we note an exponential growth both in terms of the publication and number of authors. So this has been an exciting field to work in, and it's growing very, very fast. Now, one of the aspects that is important for this presentation is the connection between Peridynamics as a non-local model to local models. So you can show, starting from the original equation, that if you make two assumptions on differentiability, one is that the formation is twice continuously differentiable in space and time, and the second one is that the force function f is a continuously differentiable function of the formation x. So without any further assumption, you can express the equation of motion in this form, which we see here the divergence of a stress tensor, which is a non-local stress tensor. However, now if we take an additional step and take the non-locality to the limit where delta goes to 0, we recover a Paviola-Kirchhoff stress tensor, which is a fundamental quantity in the classical theory of continuum mechanics. So we show here that Peridynamics under differentiability assumptions in the limit of vanishing non-locality recovers the classical theory. Now let's look into some examples. This is a one-dimensional Peridynamic model. It's a linear model, so we have C as a function of the bond, x prime minus x, is what we call the micromodulus function, and this multiplies the relative displacement, which is the displacement at x prime t minus the displacement at xt. Now, if we assume now a smooth displacement, we can use the Taylor expansions. We can expand u at x plus c, where x plus c is going to be x prime. We can expand it around x. Then we obtain the Taylor expansion, and we if we substitute this expression into the equation of motion, we can collect the terms, and now we obtain that, first of all, the terms with odd powers of c, they vanish because the domain of integration is symmetric. And moreover, what we obtain here is the leading term is the second derivative of u, followed by the other even derivatives. So now we have these coefficients, which are integrals of the micromodulus function with different powers of c. In order to proceed further, let's make an assumption on a particular family on the micromodulus functions, which is a constant c divided by the bond length to some power alpha, where alpha is going to be less than 3. With that, we can do the integration of these coefficients and obtain the following expression, where we have the second derivative plus some high-order terms, which depend on delta and the power alpha. Now, if we assume higher-order terms are negligible, comparing with the classical wave equation, we can establish a connection between the Peridynamic bond constant c and in this case, will be the classical constant, for example, E, the Young's modulus, and together with the horizon delta and the parameter alpha. And if we use this constant c back into the expression, we can write this in the following form, where the leading term gives us what we have in the wave equation, followed by high-order terms. Overall, the model discrepancy is of order of delta squared and depends on force-order derivatives. So let's keep that in mind. Moving forward, let's look into a two-dimensional case. We're going to do a similar procedure. Now this is also a linear model. Here lambda it's the micromodulus function. We have a dyadic product between the bond and itself, and we have the relative displacement as before. Here h now is the neighborhood around the origin, and if we again assume a smooth displacement and a Taylor expansion, we'll obtain a similar expression as before. It looks a little bit more complicated, but basically it's like similar integrals multiplying the even partial derivatives. Because of the symmetry of the integration domain, the odd derivatives vanish. So now, as before, if we make an assumption of a particular family of micromodulus functions, similar to before, we can obtain the final expression here, where we have two components of the displacement because we are now in 2 dimensions. And now we obtain again that the leading model discrepancy is of delta squared and depends on force-order derivatives. So far we have obtained the same result in this sense in 1 dimension and in 2 dimensions. And we are going to go back to this type of derivations later when we talk about coupling. But let's talk now a little bit about computing. So in order to compute with Peridynamics, in particular to be able to model fracture, We need to discretize the equation as usual. Now, this is a continuum model, so we can discretize with different methods. For large-scale engineering problems, normally a mesh discretization is employed, where we take a body, we discretize with a set of computational nodes in blue, and then what we do is we evaluate with a collocation approach the equation of motion at every node I, and then the integral is discretized as a summation with weights. It's a Riemann type discretization, where the weights initially they are taken as the full volume of the cell, characterizing each node in blue, but there are methods that are enhanced quadratures to improve the discretization. Now, overall, once you compute, what we would have is, for your simulations, a set of particles or computational nodes, where each node I interacts with a surrounding family of particles J, so that all points J are within the neighborhood of I. However, we can do other discretization methods, for example, of finite elements, but we are going to show now some of the simulations with this particle-based discretization. So here are three examples. First, we have on the left a projectile impact on a brittle disk. This was run with a code called PD-LAMS, which is a Peridynamics implementations in LAMS, which has been developed at Sandia National Laboratories. This was done joined with Mike Parks, where we have here the impactor hit at the center of the disk. We don't see the impactor, but we can visualize the amount of damage by coloring each computational node, as you can see here, and we don't need to track fracture surfaces, which is very helpful. The second one, it's a crack branching in soil-lime glass. This is done with a code that we are developing now at Oak Ridge National Lab. It's called Cabana PD. It's a code that runs on Leadership Club supercomputer. It's GPU-based, performance portable, and exascale capable. And what we can capture here is the crack propagation and the phenomenon of branching. And on the right side, we see a simulation we did with another code. This is a MATLAB code. It's called PDMATLAB 2D. The simulation was shown with Jeremy Trageser, that he was a postdoc at Oak Ridge National Lab, and now he's at Sandia National Laboratories. And here you can see that we can capture a complex damage pattern, capturing initiation and propagation even at multiple sites. And also, I forgot to mention that Cabana PD is a code we are developing together with Sam Reeve at Oak Ridge National Lab, which is a colleague of mine that we are working together. So you can see that we can capture all these different fracture phenomena. However, the issue is that Peridynamics is much more computationally expensive than classical continuum mechanics. In which sense? Well, once you discretize, you can note that if we choose, let's say, delta to be 1, and then we choose a discretization such that delta x equals to delta y equal delta z equals to delta divided by m is going to determine the grid resolution. So now, if m equals 1, we get, for each computational node, we get 6 bonds. When we increase m to 2, we got 32 bonds. When m is 3, we get 122 bonds. And if we now do one step of grid refinement, then we go from m equal 3 to 6, increasing the amount of connectivities for each node to nearly 1,000. So Peridynamics is much more expensive than classical continuum mechanics. So the question is, can we potentially leverage both of them together to have accuracy, but also efficiency? So the main goal of coupling Peridynamics and classical continuum mechanics is to reduce the computational cost of Peridynamics. The method to be used is to employ Peridynamics around only cracks and couple it to classical continuum mechanics. Here will be an illustration. Let's say that we have a pre-notch here, a crack that is propagating. We have a concentration here of stress. Now we can surround this crack with the Peridynamic region, and then we can model the rest of the domain with just classical continuum mechanics. Now, the challenges are going to be dealing with coupling artifacts and with adaptivity, because as the cracks are going to develop, we need to expand the domain of the Peridynamic representation. Now, other benefits of doing couplings could be, one, using classical local boundary conditions in Peridynamics, so we don't need to employ surface effect corrections that normally appear because of the non-locality. We can reduce and desired wave dispersion and be able to combine Peridynamics software with classical finite element software features. So let's go over the components for a proper coupling between Peridynamics and classical continuum mechanics. So first, we need physically consistent models so that the coupling makes sense. But this is not a problem because we already showed that we can connect peridynamics with local models in this limiting process at the beginning of the presentation. Then we need to choose a proper coupling method, which may or may not be the same to deal with static problems or dynamic problems. And then we would require model adaptivity, so we can evolve the subdomains and also identify the critical regions where peridynamics representations are required. There are other coupling artifacts that are well known, such as the patch test failure, which is the inability of the couple mode to pass a uniform strain solution problem, and also a lack of energy preservation. On the dynamic side, we also need to deal with artificial wave reflections as well as lack of conservation principles. However, we are going to discuss a couple artifact that has been kind of overlooked in the literature, and we only recently, in the recent years, we identified, which is called the lack of order equilibrium, and I'm going to give some of the analysis that deals with it. But before doing that, here is an overview of coupling methods. We have a review article on local-to-nonlocal coupling where we go over all these methods. This is done jointly with Marta Delia, Xianxi Li, Xiaoxian Tian, and Yu Yu, published in the Journal of Peridynamics and Local Modeling. And what we have done there, we classify the different coupling methods into different categories. So first, we have the constant horizon approaches versus the varying horizon approaches. Within the constant horizon approaches, we have generalized domain decomposition methods such as the optimization base and the partition procedure. There are methods that are resembling atomicity to continuum coupling methods, so we call them atomicity to continuum type coupling methods, such as the Arlechin, the morphing, the quasi-nonlocal, the blending, and the splice. On the varying horizon sides, we have the energy base, which is the shrinking horizon approach, and the force base, which is the partial stress. Now, of course, I don't have time to go over all these methods. Instead, I'm going just to focus on two, which are the blending method and the splice. So I'm going to go over those in a moment. But before doing that, let's discuss some different coupling configurations for the domain that we may need to employ. So here is a representation for a general coupling configuration. Imagine you have in one dimension a non-local mole on the left. Here you see in blue and a local mole on the right. There is a need to do some kind of transition in between. And then if we have a non-local mole on the left near the boundary, we would need to apply non-local volume constraints on the left, and you will apply local boundary conditions on the right. In two dimensions, we may have a system like this, where it's an embedded subdomain, where the non-local mole may be surrounded by the local mole, and in between there is a transition region in green. And in this case, for example, one would be able to apply local boundary conditions because we have the local domain near the boundary. So here are some more configurations for the different methods. So this is a domain decomposition with overlap. So there is an overlap between the non-local domain and the local domain. Here is an illustration in 1D, and we have two potential configurations here in 2D, adjacent subdomains or embedded subdomains. And the methods that employ these configurations are the optimization base, the partition procedure with overlapping, and the Arlechin. And I just want to give you a brief overview of this. The next one is a domain decomposition without overlap, but with blending. So there is no overlap, but now we have a region where we blend the models. And this is the region here, the bridging region in yellow. And there is also some region around it with the width of delta that we also need to consider. The methods that use this type of decomposition are the morphing and the blending. And again, the blending is one of the methods we will discuss later. Then we have a domain decomposition without overlap and with no blending. There is still some kind of a transition domain here. And these methods are used, this decomposition used for the partition procedure with non-overlapping approach. The quasi-nonlocal, the splice, will be with an empty transition in this case, and the partial stress. And then finally, there is this domain decomposition with a smooth local-to-nonlocal transition where, in fact, the length scale delta is going to shrink towards the interface, and this is used by, as the description suggests, the shrinking horizon approach. So now that we have seen all these different approaches, let's focus on one of the methods, which is the blending. So this is the peridynamic equation of motion for a linear bond-based peridynamic model, which relies on pairwise interactions. It's kind of one of the simpler versions of peridynamics. So in this case, we have the micromodulus lambda, the dyadic product of the bond, and then we have eta, which is the relative displacement. And what we can do now, if we look into the bulk of the material, meaning all points x that are far from the boundary, so that their neighborhood is fully contained in the domain, then we can expand the relative displacement as we have done at the beginning, obtain the Taylor expansion, and when we replace eta in the equation, we obtain the classical equation of elasticity. In this case, lambda has the following expression. It relates, the expression relates lambda, capital lambda, with the micromodulus function, and also the lambda is related to the classical constants, such as the Young's modulus. Now, what we would like to do is to take this non-local model, which is the peridynamic model, and couple with classical elasticity, which is the local model. So let's, for simplicity, start with the one-dimensional model. This is a peridynamic linear model that, under the following constraint here, we know that for smooth displacement, neglecting higher-order terms, we recover the classical elasticity wave equation. So the question is, how can we combine the peridynamic and the classical elasticity in a single model? So we can do a first method with like an ad hoc type of coupling, where we divide the domain into a peridynamic region, the classical elasticity region, and a bridging region in between. We can introduce a blending function which takes a value of 1 in the peridynamic region, 0 in the classical region, and between 0 and 1 in the bridging region. And now we can just do a weighted average of the two models, where we combine the blue non-local model and the red local model with the weight beta and 1 minus beta. So this sounds like a reasonable procedure, except that we immediately see that we are losing the antisymmetry of the non-local integrand, and now the Newton's law does not hold in general. So we'd like to see if we can do something a little better. So instead of taking two models and enforcing some ad hoc combination of those, we are going just to start with the single equation, which is the non-local peridynamic model everywhere, and we're going to make some assumptions leading to the coupling. So first, we start with the full peridynamic model everywhere, and then we introduce a symmetric weight. So we're going to add and subtract the same term. So now we are retaining the symmetry of the non-local integrand, and then we take the complementary term. Now, what we're going to do now is we're going to define an internal subregion inside the peridynamic region farther than delta from the transitions. And what we note, for example, if we look into a particular blending function, let's say piecewise linear blending function, which is 0 in the local regions and 1 in the peridynamic region, we know that if the point x is far enough inside the peridynamic region, the value of beta is 1 for x and 1 for every neighbor of x. And that means that the second term would not contribute. So what that means is that we can safely assume that the second term only contributes in regions that are far from the inside critical region inside the peridynamics. And if that's the case, we can make an assumption of smoothness for those regions as normally done, and we can do a Taylor expansion and now replace the relative displacement only in the second term, because we are safe to do that because of the previous description. And once you do that, now we can obtain the non-local integral, and then we're going to obtain a term with the first derivative and a term with the second derivative. So here is the final expression. We have the non-local term in blue with a symmetric weight. We have in red the local term with a weight involving an integral over this blending function. And then we have, for free, we obtain this coupling term that depends on the first derivative and also has a weight of an integral of the blending function. Now, this model overall gives peridynamics when beta is full 1 and classical elasticity when beta is 0. The non-local integrand is antisymmetric and its patch test consistent, has no ghost forces. Now, the new idea here was that we derived the blended model using the properties of peridynamics, in particular its connection to classical elasticity, instead of trying to directly attempt to couple two separate models. Now, looking into higher dimensions, we can do a similar procedure. Here is the linear bond-based peridynamic equation with the micromoles function lambda. We have the corresponding local limit, which is the Navier equation of elasticity. And then we can do a similar procedure, and we are going to obtain a similar expression where we have the integral non-local contribution with a symmetric weight, attain with the first derivatives, and attain with the second partial derivatives. And here, CILJK is the first order stiffness tensor. We can additionally estimate the mole error by now bringing back all the high order terms that we have neglected. And with that, we can bound those extra terms to account for the error. And we obtain that there is a term containing the third partial derivatives and the fourth partial derivatives. Now here, note that the definitions are beta overline is the maximum value of beta for points in the surrounding or the neighborhood of X, and beta underscore is the minimum value. And what we observe is that, in fact, the first term with the third partial derivatives, they only contribute in transition. So whenever you are far enough in the classical region, this does not contribute. So it makes sense that we are getting the first order derivatives, which what we have observed at the beginning of the presentation, as the next terms in the expansion. So let's look into one example. This is going to be a static example. Here is the static peridynamic equation. We have a particular micromoles lambda that is related to the Young's modulus, and the classical mole is given here, where the notation is that U has V as the X component and W as the Y component of the displacement. We're going to look into the problem of a square plate with a rectangular slit, like a hole at the center, and we're going to apply traction and shear here. So you can see we pull up and to the side, and we are going to look into the deformation of the plate. We are going to employ the blending approach, where we surround the slit, which is the critical region for us, with the peridynamic region. We have a bridging region in between, and then outside we have the classical mole, so we can apply classical local boundary conditions. And here is the result. We have on the left the classical mole, in the middle the blended mole, and on the right the peridynamic mole. In the bottom we have a zoom in to the region around the slit, so we can better visualize the deformed slit. Now what we note is that if you look into the peridynamic result on the right, we see that far from the slit, things look very, very similar to the classical simulation. That means that we should be able to replace the descriptions on the peridynamic regions far from the slit with the classical description for expediency, and then combine the two through a blended approach. This allows us to obtain a very similar result as what we have seen in Peridynamics, but at a much cheaper cost. In this case, the classical one is very quick. It's just 2 minutes. Peridynamics takes about 4.3 hours. And when we combine the two, we can obtain what we would like to have a reference peridynamic result, but at just 24 minutes. So it can be much, much faster. Let's move now into a second and different approach. It's called the splice. This is probably one of the simplest ways to couple peridynamics and classical continuum mechanics. What we do, we just simply have an operator that takes either of two forms. Whenever a point is in the peridynamic region, we use the peridynamic operator, and where the point is in the classical region, we use the classical operator, and there is no specific operator in between in the transition. Now, in the discrete formulation, we would have something like here in 1D, finite elements on the left, and peridynamics, let's say a mesh discretization, we have peridynamic nodes on the right, and now where the point is like every peridynamic node will only see a peridynamic mole. So when I am a green node, I'm going to interact with nodes surrounding myself, either if they are finite element nodes or peridynamic nodes, through a peridynamic operator. And when I am a finite element node, I'm going to interact with my nearest neighbors through a finite element operator. Now, even though there is no really a transition region, we can still define like a coupling zone wherever there is an interaction between peridynamic nodes and finite element nodes. Now, here is a discrete version in 1 dimension. We have the displacement vector, and then on the right side, we have the forces. We have the stiffness matrix here, where on the top we have the finite element description, which is tridiagonal. And immediately, because there is no transition, we jump to, in this case, a pentadiagonal system, because M is chosen to be 2. And we see that there is no transition in between. Now, let's remember this system because we're going to use it later on. So remember, we have the displacement with the stiffness matrix, and then on the right side, we have the force. And we are going to get back to it in a few slides. Now, you can show that this type of coupling, the splice, is consistent for a linear patch test. We pass the linear patch test and a quadratic patch test, where we look into some relative error measured in this way. So the splice method really passes a linear and quadratic patch test. However, we are going to look into a problem that has to do with overall equilibrium. So this problem can be described as follows. Let's look into this rectangular domain. We have some supports on the bottom, and then we apply a concentrated load on the top. If we solve this system only with finite elements, as you can see in the table at the bottom, we obtain a negligible relative error. Similarly, if you solve it just fully with peridynamics. However, when we couple the two, you obtain a non-negligible error. And we would like to see if we can understand this error so we can control it. To do that, let's go back to a one-dimensional case. Consider the classical model. Here is a static model. We have the domain from 0 to L. This is the body. And then we can integrate the equation over the entire domain and to obtain, as a result, the following local balance equation, where the tractions on the boundaries balance the external forces. So the boundary local tractions, they balance the external forces. We can do a similar approach when we have a non-local model, a peridynamic model, where we now have a non-local boundary here on the left and on the right. And if you look into the static equation, we again can integrate the equation over the domain, and using a definition for a non-local traction, we can still obtain a non-local force balance equation where the non-local tractions balance the external forces. The question now is that if we put the things together so that we have peridynamics in between, surrounded by two local regions, what results are going to obtain? Are we going to obtain an overall equilibrium or not? So in this case, we have in the classical regions, we use the classical equations, on the right and the left classical regions, and in between we use the peridynamic equation. The way to proceed now is we are going to integrate each equation over its respective subdomain, and then we're going to add the equations to obtain a final coupled force balance equation, where the local tractions on the boundaries plus the external forces are not necessarily 0, but instead they are equal to a combination of local and non-local tractions at the right and left interfaces. So overall, the conclusion is as follows. We know that the net force applied on the body is the summation of the tractions plus the external forces, and because of the previous expression, this net force is equal to this combination of local and non-local traction at the two interfaces. Now, overall equilibrium requires the total force to be 0, meaning that we need balance of local and non-local interface tractions. Now, in order to be able to better and more detailed describe the discrepancy here, then let's look into a particular family of micromodulus functions. So now we can expand the non-local traction as the local traction plus additional terms. And if we plug this back into the expression for the total force, what we obtain is an expression where the leading term depends on delta square and the third order derivatives. So if you remember now, comparing to what we got in the model discrepancy at the beginning of the presentation, which was order of delta square and dependent on force order derivatives, instead here, the model coupling error for the out of balance has an O delta square error and depends on third order derivatives. Let's look into 2 dimensions now. Now we have a more complex domain. We have the classical equation. We can integrate over the domain and obtain a local force balance equation again, so that the boundary local tractions balance the external forces. Similarly, in 2 dimensions, we have now a collar of with delta, a non-local boundary region. We have the static equation, and if we integrate again over the domain, we obtain a non-local force balance equation with the non-local tractions. balancing the external forces. Asking the question one more time, what happens when we couple these things together? We can look into the following configuration, an embedded subdomain description where the peridynamic mole is surrounded by the classical mole and there is an interface gamma in between. Now the classical equation is used as in the splice for the classical region, the peridynamic equation for the peridynamic region, and now we obtain, by integrating each equation over its respective subdomain and adding the equations, we can obtain a couple force balance equation where overall we obtain that it's not necessarily zero, but it's equal to an integral with a minus that is over the interface, the model interface here, and it's a combination of the local and the non-local tractions, similarly to 1D. However, we're going to see that the result is slightly different. Now, first, going back to this idea of the net force, we know that the net force upon the body is the sum of the tractions and the external forces. Therefore, it's going to give us this expression of the negative of the integral over the interface gamma on the combination of local and non-local tractions. Overall equilibrium requires the total force to be zero, meaning that we require balance of local and non-local interface tractions. If we look into a case of, let's say, a straight horizontal interface, we can again expand the x and y components of the traction to obtain expressions which are leading by the local traction plus some additional terms, and when we plug this back into expression for the net force, we obtain these expressions that overall now they are O of delta squared, but they now depend on second order derivatives. They are O of delta, not delta squared, and depends on second order derivatives. And similar results can be obtained for a vertical interface, so I'm going to skip. Now, the question is, going back to the one-dimensional problem, what if these high-order derivatives that give us this overall, the errors, overall equilibrium errors, what if we cannot neglect this? To explore that, let's look into a one-dimensional case where the peridynamic region is surrounded by two finite element regions. This describes like a one-dimensional bar. And then what we are going to impose a particular deformation on the nodes. This is the system I anticipate that we're going to look at it again. And we're going to compute the forces for a given displacement field. With these forces, we can compute the relative error. And the displacement field we're going to impose is a piecewise profile, which has two linear profiles, curve 1 and 3, connected with a cubic profile. And what we are going to do, we are going just to change the location of this cubic profile so that whenever it is in the finite element region, we get negligible error. Similarly, when it is fully inside the peridynamic region, but when it is in a coupling region, we obtain a not negligible error. So we already demonstrated that if the third order curve is in the coupling zone, the out-of-balance error is not negligible, and this is consistent with our analysis of the coupling error in one dimension that depends on third order derivatives. Additionally, we can look into convergence. First, looking into M convergence, which means I'm going to take delta to be fixed, and I'm going just to increase M. Now, the error doesn't change significantly because the error really depends on delta. But if now do a delta convergence where M is fixed and delta decreases, you see that the relative error here is really constant. So the error decreases, but overall, the error divided by delta squared gives us a constant value. So the net force reduces with the horizon as O delta squared, which we already knew from the theory and the analysis, but now we confirm numerically. Looking into a two-dimensional problem, we can look into a peridynamic region surrounded by a finite element region. So this is like a plate. And what we're going to do, first we're going to apply a bilinear displacement over a straight interface, and then a quadratic displacement over the interface. And again, we can confirm that when we have this bilinear deformation over the straight interface, the errors are negligible, but when we apply the quadratic one over the interface, then the error is not negligible, and this is consistent with the fact that errors arise with second-order derivatives over the straight interface. But more interesting is that if we look into applying a deformation over a corner, in this case a bilinear deformation, now we do see errors, which brings the insight that now the error is not just dependent on the deformation, but it now depends on the shape of the actual interface. So overall, we obtain that second-order derivatives over a straight interface gives an out-of-balance error, which is not negligible. And first-order derivatives over the interface corners brings an out-of-balance error that is also not negligible. Let's finalize here with an application example. We have a plate, a three-point bending example with two supports, an applied load on the top and a pre-inertia on the bottom. We are going to use an indicator for second-order derivatives because these are the leading terms for errors in 2 dimensions. This is expressed here where we compute these partial derivatives with the peridynamic differential operators. And this is useful because, for example, you see here the illustration where we visualize this operator and give us a high values on the supports, on the crack tip, and on the place we apply the load. So we obtain that we have high concentrations of this gradient around the crack tip, for example. And because of that, what we are going to do, we are going to apply a decomposition of the domain so that we have peridynamic nodes surrounding the crack, in particular the crack tip, and outside there is a transition to the finite element nodes. Now, because we know that errors depend on these high order derivatives, we would like to explore how far one could have the interface from the crack. So we assume that, and we hypothesize that if our interface is farther from the crack, then we are going to have the errors more control. And what we are going to use here is a switching scheme. So as long as the crack propagates, we are going just to change peridynamic node, finite element nodes into peridynamic nodes. Here is the adaptivity in time for different steps. We have the crack propagates, and then the two interfaces correspond each one to a different switching scheme. They evolve with the crack. And you can see here, for example, in the step 1000, that the switching scheme 1 has an interface already over a region with high gradients, and we already knew from the previous analysis that that would lead to coupling errors. So if you look into the out-of-balance forces, for the switching scheme 1, we see the errors kind of increase compared with the low step. With the switching scheme 2 in blue, that needs much more control. So the conclusion is here that knowing in the information of these high order gradients, they can help us to drive model activity to reduce out-of-balance forces. So let me summarize this presentation. So we gave an overview of coupling, discussing peridynamics and classical continuum mechanics. The main motivation was to reduce the computational cost of peridynamic simulations. We look into coupling methods and configurations. In particular, we describe in detail the blending and splice methods, and we perform an analysis of the overall equilibrium. And we show that we have an application for coupling adaptivity based on our analysis. Here are some references. First, this is a reference for the review article on the journal of peridynamics for the overview of the coupling methods. For the blending, there is 3 references here that are available in the literature. There is 1 reference here for the splice that I have used, and we have another publication in Computer Methods in Applied Mechanics and Engineering for the treatment of the overall equilibrium problem and analysis. And I bring here 1 more reference, which has to do with coupling as well in the context of interface problems in non-local diffusion. Let me just conclude here by acknowledging the funding support. So we have the different funding supports for the overview of coupling, funding support for the development of the coupling methods, and funding support for the coupling analysis. So we are very grateful for all these sources of funding. At this time, I would like to thank you for your attention, and I'm happy to answer any questions you may have. Thank you.
Thank you very much. That was actually a quite thorough talk on the coupling side of local and non-local. For questions, please raise your hand. I'll call out your name as they appear on my screen. You may also unmute your mic if you're not able to raise your hand. Okay, I do not see any raised hands, so probably I'll ask 1 or 2 trivial questions. So that coupling part was largely clear to me and quite enjoyed it. But I was interested in learning about your code Cabana because I understand there is another code, Paradigm. So what is the difference between the 2 capabilities?
That's a very good question. So Peridym, it's a code developed at Sandia National Laboratories for Peridynamic simulations. It has a lot of capabilities, and this is one of the two codes that has been developed, such as PDLAMS and Peridym. Cabana is a much newer code we have developing at Oak Ridge National Laboratory. One of the features of Cabana PD is built on libraries that allow us to do very efficiently large-scale simulations and leveraging GPUs. So that's one of the main things that happen, and we can also have performance portability, meaning that because we are developing it on these libraries, we can naturally, without having to do an extra effort, run it on different machines. So we have GPU capabilities, performance portability, and it runs very efficiently on these large machines. So it's redeveloped so we can tackle very large problems.
I see, I see. So at the back end, okay, I'm not sure if Taylor or Petsy has GPU support or not, but what are you using what libraries are you using?
So we are using CUDA for GPUs on Summit and HIP for GPUs on Frontier. And the one I would say, as far as I know, Peridym is mainly just CPU based. So that's kind of
Okay,
one of the big difference.
okay, but what is the linear algebra library that is using CUDA that you're using it?
Oh, that I'll have to look into that to give you back the information.
Okay, fair enough, fair enough, fair enough. Are there many more questions or comments? You may unmute your mic.
Yeah, and maybe just to
Yeah.
add on that. So we are really excited about this capability. Uh,
Mm-hmm.
because we built it initially to run very robustly in these machines.
Yeah.
And now we have several projects that we are increasing the physics applied, the physics modeling capability of it. So we are going to see more and more complexity in terms of physics modeling added in the next few months and the next couple of years or so. So we are really excited about this capability.
Yeah, it does. Yeah, it does sound very exciting. I mean, probably that's one of the few libraries that works on non-local for on a large scale problem. So for sure, it's very exciting.
And just to make sure, it's an open source code. So
Mm-hmm.
both, so we have Kavana PD is open source. We also have PDMATLAB 2D in case
Mm-hmm.
someone would like to just do two-dimensional dynamic simulation in MATLAB,
Mm-hmm.
which something is more amenable for people that just started. Both of them are open source and available, and I'm happy to share the links so someone can contact me if they would like to access those.
Yeah, you may share your that would be nice if you could share your link. So what I do when I send out the YouTube lecture of yours, I can actually attach your links in the same same email because I mean software resources would be very nice to have spread across within the community.
Yeah,
So
we're really happy to people using those, and they can help us test those capability and increase their modeling
yeah.
capability.
Yeah, fair enough, fair enough, fair enough. I'm of a very similar view on that matter. I mean, I'm writing my own. I've been writing my own codes, but the equations that I have are far more complicated because these are fractional Navier-Stokes type equation. So yeah, so I may ask you at some point. I may actually get in touch with you,
Yeah,
touch
that would
with
be
you.
great. Yeah.
Yeah, it's like how to solve this equation on a larger system. Okay. Okay, if you can just, send me those links, when I send out the YouTube lecture, I can actually attach it to it.
Yeah, sounds great. Yeah, I'll do it.
Sure, sure. Uh, all right. Are there any more questions or remarks? Probably no. So I believe this is a very good point to close this seminar series and your talk as well. Thank you very much for again, Professor Selson, for joining us. It was very nice having you.
Yeah, thank you very much for the invitation. It was a great pleasure to be here. Thank you.
Yeah.